Previously, we've alluded to light as being a wave. Light in fact has a dual nature that can be described as both a wave and a particle. The particle nature of light is evident when a ray of light, which can be visualized as a stream of particles, hits an object and causes a shadow. The shadow is a region where the light particles are blocked from striking by the object. However, for other observed properties of light, it can only be described by considering the wave properties of light. In the subsequent videos, we will predominantly investigate this wave nature of light. When we first introduced the concept of waves, we described waves as being a disturbance that transports energy from one place to another. In mechanical waves, this disturbance is through some medium, such as water for water waves or the air for sound waves. In light, there is no medium that is disturbed, but rather the disturbance are electric and magnetic fields. Thus, light is called an electromagnetic wave, or EM wave, in which electric and magnetic fields vary sinusoidally with each other. So light can be described by the general wave equation, where the electric field E is equal to EM cos of kx minus omega t, and the magnetic field B is equal to BM cos of kx minus omega t, where EM and BM are the maximum electric and magnetic field amplitudes, K is a wave number, and omega is the angular frequency. It was James Maxwell who realized that the changing electric field could create a changing magnetic field, which would then in turn create another electric field and so on. The result would be a self-sustaining electromagnetic field that is endlessly repeated as it travels at an incredibly fast rate through space as depicted in this animation. Note, however, that the magnetic field is not to scale. The amplitude of the magnetic field is in fact 300 million times smaller than the amplitude of the electric field. Maxwell estimated the speed of light, or any other EM wave for that matter, to be around 300 million meters per second, which is pretty close to the most recently experimentally determined value of 299,792,458 meters per second. In most cases, the speed of light is approximated to be 300 million meters per second, or 3 by 10 to the 8 meters per second. Maxwell's theoretical analysis of the wave nature of light was soon confirmed experimentally by German physicist Heinrich Hertz. Hertz generated and detected electromagnetic waves, a discovery that has led to many practical communication systems including radio, television, mobile, and radar. The unit for frequency is named after him. Furthermore, Hertz and other investigators showed that these waves exhibited reflection, refraction, and all the other characteristic properties of waves that we will further explore in subsequent videos. We now know that there is a whole spectrum of electromagnetic waves, each distinguished by their wavelength and corresponding oscillating frequency. At the lowest end of the spectrum, there are highly oscillating, high-energy gamma rays that have wavelengths much smaller than the size of atoms. At the other end, there are low-energy radio waves whose wavelengths can be as long as many kilometers. Most practical communication systems, such as radio, television, mobile, and radar, are based on propagating EM waves with wavelengths as short as 6 centimeters, as is the case for Wi-Fi networks, or as long as hundreds of meters, as in the case for AM radio. Irrespective of how large or how small the wavelengths of the EM waves are, they all travel through space with the same speed at 300 million or 3 by 10 to the 8 meters per second. We saw when we explored the properties of wave motion that the propagation speed of any wave is proportional to its wavelength and its corresponding frequency, and is given by the formula V is equal to F lambda. The speed of light, or an EM wave in a vacuum, is given the symbol c to represent a constant, as this speed is fixed and sets the limit for the fastest speed of anything in the universe. Nothing travels faster than the speed of light in a vacuum. This formula can be used to convert the wavelength of an EM wave into its frequency and vice versa. For example, the Fox FM radio station broadcasts a signal on a carrier frequency of 101.9 MHz. So what is the wavelength of this radio signal? Our eyes are sensitive to light, which lies in a very small region of the electromagnetic spectrum, called the visible spectrum. This visible spectrum corresponds to a wavelength range of about 400 to 700 nanometers, where 1 nanometer is equal to 10 to the negative 9 meters. Our eye registers these wavelengths as colors in the range of violet through to red. The human eye is not capable of seeing radiation with wavelengths that are outside the visible spectrum, so we cannot see ultraviolet or infrared light or radio waves, for example. White light is a mixture of all the colors of the visible spectrum, while black is the total absence of light. Earth's most important energy source, the Sun, emits light that consists of the entire electromagnetic spectrum. You might wonder, however, why we can only see this range of the electromagnetic spectrum and not other wavelengths. Firstly, vision usually involves some kind of chemical reaction triggered by the quantized energy bundles, also known as photons, of the EM radiation. The carbon-based chemistry of our cells happens to correspond to excitation induced by light that oscillates at frequencies in the visible part of the electromagnetic spectrum. The energy carried by the EM waves is given by the equation E is equal to hf, where h is Planck's constant and has a value of 6.63 by 10 to the negative 34 joules seconds. The Planck constant is named after German physicist Max Planck, who is considered one of the fathers of quantum mechanics. Secondly, EM waves in the visible part of the spectrum can travel quite far in water before they get absorbed, which is why a cup of water looks transparent to us, since almost all the visible light passes through it. The first eyes evolved from under the sea, and so this range of wavelengths held the most evolutionary advantage compared to other wavelengths. So when we see the color violet, that means our eye is responding to the energy of the EM wave that has a wavelength of 400 nanometers in air. So what is the frequency of the violet radiation? And how much energy is carried in each energy bundle or photon at that frequency? In summary, light is a traveling sinusoidal wave of electrical and magnetic fields of a given wavelength and frequency. Light is the electromagnetic radiation that falls in the range of 400 to 700 nanometers in the electromagnetic spectrum. We see this visible radiation as colors ranging from violet to red. The speed of light through space or a vacuum is constant at 3 by 10 to the 8 meters per second. Light carries energy in discrete units called photons. The amount of energy in each photon is proportional to the light's frequency and is given by E being equal to hf, where h is Planck's constant and has a value of 6.63 by 10 to the negative 4 joules seconds.